Today's video will demonstrate how to implement the four different command passing design patterns. Hello, I'm James Helfrich. There are four fundamental ways to pass a command from one part of the program to another. The first, direct invocation. The second, delegate. The third is command, otherwise known as encapsulated. And the fourth is interpreter. This video will demonstrate all four in the context of the game of Sudoku. Okay, the first thing we need to do is talk about the three parts of any command passing scenario. There's the commander who initiates the order, there's the executor who executes the order, and then there's the order itself. And each of these is going to change slightly according to our four different command passing design patterns. We'll begin with direct invocation, and this is the default way we use to send orders. This is how we've been passing commands from one part of a program to another for years and years since the very first program we wrote. This is basically a function call. And so what we have is the commander is going to have a bunch of different places where to execute the function, and the executor is going to receive those direct function calls each one at a time. So let's see how that looks in the game of Sudoku. So first I'm going to demonstrate the game of Sudoku, and then we're going to see how the command passing design pattern relates to it. And now we have the game of Sudoku. Notice I have a little menu. I can question mark to show these instructions, D to display the board, E to for edit a square, S to show the possible values in the square, and Q to save. And all this happens in the function called to interact, where I prompt the user for a command, and then I do a question mark to display options, a D to display the board, E to edit the square, S to display possible values, and so on. Observe that the function display options is immediately called when I call the function. Now, of course, this is the default way in which one part of the program commands another part of the program to do something. But notice that this is synchronous. In other words, the execution of interact is paused until display options has finished its job, or display board or edit square. And then we continue to do the next again synchronously, and we interrupt the caller until the callee has returned. This is direct invocation. So we have a second method to do this called delegate invocation. And this is the process of sending an order in the form of a function pointer. So we're going to start with the commander, and then of course we're going to have the executor. And the commander is going to send the executor an order in the form of a function pointer. And so A, and then B, then C, then D, all the different parts of the program can create this order and send it to the executor through a single pipe. Let's demonstrate how that works in Sudoku. So here's our original design, which has, well, many function calls, but we're going to focus on just the interaction between interact and the four different kinds of interactions: display options, display board, edit square, and display possible. Now, what we're going to do is, first of all, we're going to introduce a function called execute, and then execute will call display possible directly, as well as call edit square and display board directly, and display options directly. Now, what's going to be the connection between interact and execute? We're going to pass the order as well as the board, which is the context, and then execute will then pass the board on to every single function. Okay, the first thing I need to do is have some mechanism to represent a function pointer. And in C++, the syntax for that is kind of nasty. Okay, this nasty piece of work is a function pointer. The variable is actually right here, order, and this is a pointer to a function, and that function returns a void and takes a board by reference as a parameter. And initially, I'm going to set it to the null pointer. Now, the next thing I want to do is assign either display options or display board or edit square display possible to this order, depending on what the user selected. Okay, so let's see what we did here. I'm going to assign the display option function pointer to the order variable. Now notice how there's no parentheses. I'm not calling the function. I'm saying give me the address of. C++ actually allows me to either do the address of or not. In either case, I'm still assigning the function pointer to this variable. Now the next thing I want to do is I want to actually execute this function. Okay, let's take a look at this execute function. I'm going to take the order as a parameter, which, remember, this is a function pointer. I'm also going to take the context, what I'm going to modify, in this case, the board, and I'm going to say if the order is not the null pointer, because I'm going to default as null pointer, then execute that function. So the last step, of course, is to call this, and then I will do that right here. Okay, now I have the delegate design pattern. Let's run it to make sure that it works. Where's my board located? Board.text. What is the possible values for E5, it looks like it's 8. And so I was able to execute that order exactly right. Okay, so this was delegate invocation. In other words, I pass a function pointer from one part of the program to the other, and the executor will execute it on my behalf. It's kind of silly in this case because I'm doing it right away. There's really not a big advantage over direct invocation, but we're going to still follow this pattern as we develop more sophisticated design patterns. And so the next one is encapsulated. Here, the order is not coming across as a function pointer, but rather as an object. And this object is going to have a function in it as well as the context. In other words, all the information necessary to execute that function. And so I'm going to have the same commander, I'm going to have the same executor, except this time the connection between them will be an object. And then each of the different parts of the commander is going to formulate the order and is going to send it to the executor, and the executor will know how to unpack and execute that object. So let's take a look at how that's going to play out in the game of Sudoku. So we're going to start with where we were with the delegate. We have the execute function, and then we're going to have all four of the different options here. Except now, instead of passing the delegate as well as the context, we're simply going to pass an order. And then from execute to the four possible functions, we're going to pass the context as we did before. So now we're going to have an order class, and that class will have a single method called execute, and it's going to be a pure virtual function. Therefore, this is an abstract class. And then we're going to have a derived class called this order display. And display doesn't actually need to have any context because I'm just going to display the options. Order edit will have to have the board, so that's going to have be the context in it. And then order possible moves is going to also have the board as an attribute. And now my order will be fully fledged, has all the information necessary to execute it. So now the execute method becomes much simpler. Okay, the first thing I need to do is create an order class. Okay, observe my order class. First, I have a constructor to make it easy to create the order. Then I have an execute function, which will execute the order, and I keeping the context with me, the board. Now, right now, this order doesn't do anything. My execute is empty. I'm going to create a collection of derived classes, each one referring to the different types of orders I would want to create. And let's see what my derived class are going to be: display options, display board, edit square, and display possible. Okay, I created my first order, and notice how I made execute a virtual function, and now my order options will implement my execute, and it will just call display options. I'm going to do the same thing for the other orders as well. Okay, now I have one order for every different type of action I want to do. So now I'm going to modify my execute to now accept the order rather than a function pointer. Okay, now notice how when I call execute, the order stands on its own. I don't need to pass another parameter. That makes my execute super easy. Notice how I can create the order for each individual case, and it's self-contained. I can actually go a step further to make this a little bit more elegant. So for both edit square and display possible, then we have to ask the user what square do you want to edit or what square do you want to know possible. And I'm going to put all that code into the order so the order is completely self-contained. And that's kind of my goal here. Now notice that my execute just simply calls the other function. I'm going to actually move the code into that function to reduce one extra function call. Let's do that real quick. Okay, looks like it worked. And let's see here, edit a square. And I'm going to square to edit E5 and make it the value 8. And sure enough, everything works exactly as before. So going back to our original design, now that we have a fully encapsulated order, we could do something pretty cool. My interact function can actually remember all the different orders that were executed. And then I can display everything that was executed up to this point with the show history, and I can even perform undo. And now I'm going to do one more thing, which is really going to bring out the power of this command passing design pattern. I'm going to have a get name. Let's implement these for each. So I have a get name. Now I'm also going to have an unexecute. We're going to see what that means in just a minute here. Okay, so for my edit square, notice how my execute prompts the user for information and then for the location and for the value that's going to go in, and then I put the value in there. I'm actually going to move this into the constructor, which means I need to have both a coordinate and I need to have a value as part of the attributes. So I'm going to add these as attributes real quick. Now in the constructor, I'm going to move the code to actually get these values. Okay, what does this mean? That when I create the order, I'm going to completely fill it out with my extra attributes. And when I execute it, I will only execute something if the value is not -1. That's super important. So now when I say get name, I'm going to show the actual coordinate and the actual value that is going to be changed. So if my order edit, what is my get name going to do? It's going to return the coordinate before and then followed by the value. And all this will be in a single string. So this is going to show me exactly what order's going to be executed. I'm going to do the same thing for possible values. Okay, so it works. So you may ask yourself, why bother? What is the advantage? Well, now that I fully encapsulated an order or an action into a single variable, I can create an undo stack and a redo stack and display all the actions that have happened previously all at once, which was impossible to do with direct invocation. But now, since every order is in a single variable, this becomes trivial. First of all, we're going to display our actions, and then we'll do the undo and redo. Okay, let's see how this works. I've created a new option called H, and it's going to walk through all the possible actions in my collection of actions, and it's going to display the get name. And let's see how that works. Is every time I execute an order, I'm going to push it back or I'm going to remember it just before I execute it. Okay, let's run it. So let's see here, my board.text, and I think I'm going to edit E5, and I'm going to put the value 8 in there. Then I'm going to display the board. And let's see here. I'm going to show the possible moves for D1, and that's going to be 4. So I'm going to edit D1, and I'm going to put 4 there. I'm going to display it. Okay. So now I did 2 actions, well, actually more than that. So if I say history, it looks like I edited E5 and put the value 9 there. I displayed the board. I show the possible moves for D1. I put a 5 in D1, then I just called display board again. In other words, I was able to remember the history. Now let's see if we can perform undo. Wouldn't that be cool? In order for undo to happen, I must have an opposite action for every action. In the case of Sudoku, it's easy because the only thing that actually does anything is going to be to edit a square, and then I'm just going to put a 0 there, which indicates that particular square is not busy. So that should be super easy. So I already have my undo, and my undo is going to be empty for everything except for 1. Okay, I think I finished this. So now let's take a look at my undo. So I say if my actions are not empty, then I'm going to execute the undo. I'm going to delete the actions because don't forget I allocated my order. And then I'm going to pop it back off the stack. Okay. Um, Now let's run this to make sure it works. I'm going to give myself lots of space here. So, type the wrong spot. Board.text is my board. I'm going to edit E5 and I'm going to put an 8 there. I'm going to edit B2 and I'm going to put a 1 there. And I'm going to show possible values for H2. It looks like it's only 7, so I'm going to edit H2 and put 7 there. Let's take a look at my history. So I have 3 edits and a show possible values. So I'm going to display, and you'll notice that I have a 7 in H2. If I say undo, I'm going to undo my display board, okay? I'm also going to undo that H2 to put the value 8. So now when I show my undo stack, then I'm just going to have 2 edits on there. When I go display, look at that. It's empty. That's cool. So I'm going to show my history here. I'm going to undo my display board, undo my show possible moves, and now I'm going to undo my B2 to 2. And so I should only have 1 edit, and so this is now empty, but I still have the edit here. So now I should have 2 elements of my undo stack, the edit here and my display. So if I show my history, so I'm going to I'm going to undo my display board, undo my E5 to 9. When I hit display, then guess what? I'm back to where I was before. So isn't that amazing? Undo is such a cool thing. All I have to do is create something called an undo record, and that undo record is an encapsulated order. This is a whole ream of functionality that I never had the possibility to do before when I did direct invocation, but encapsulated invocation gives me that possibility. How cool is that? Okay, so this was encapsulated invocation. Now, the last thing we can do is the interpreter. And the idea behind the interpreter is I want to take the order, but I want to encode it in text. In other words, I don't want to pass it as a pointer. I don't want to pass it as an object. I want to pass it as a text. And this text means that I can send it across the wire between 2 different problem domains because I can't send a pointer from the client to the server because the server is going to have a completely different address space. So I got to serialize this information. And we actually have a pretty big history of how we do this. For an example, I can say, I can encapsulate my order in a selection of numbers. Number 3 means do something. Number 1 means do something else. Or I could do it textually, and this is simple mail protocol, how I send it from an email client to an email server. I can set it as section parameters, and this is how we do the command line processing. I could do it as a parse command. This is like Smith notation for chess. I could do a data interchange like XML or JSON. And I can even have a context-free grammar that's super rich, for an example, SQL. All these are different examples of trying to take an order and encode it in text so that I can pass it over the wire between problem domains. So now I need to come up with a language for Sudoku. And so I have basically 4 different kinds of orders. I have options, I have display, I have show possible moves, and I have edit a square. So options I can just represent with a simple question mark. If I see a question mark, then display the possible options the user can do. If I see a D, then I will display the board as it currently stands. If I show possible moves, I want to show the possible moves, but for a specific square. So how am I going to do that? Well, I'm going to say S is my leading letter to mean show possible, and D1, which means show possible values for D1, or SE7 for show possible values for E7. Now, the last type of order is to edit a square, and I need to represent both which order is with the letter E. I need to show the coordinates of which square I'm editing, as well as the value I'm going to plop into there. So for an example, E, A4, 8 is going to place the value 8 in A4. And then E, G7, 3 will place the value 3 in G7. So let's say, for an example, I have a Sudoku board that looks like this, and then I execute these 5 different orders, which is I'm going to place 4 values, then say display, then my new board will look like this. Let's do the easy stuff first. Like I want to know the options, so I'm going to say order equals string. I mean question mark. And if the first letter is a question mark, then that I'm just going to display the options. All right, now when I create the order for edit a square, I need to bring all that code in that I had before about generating the D4 to put 5 in there. So I'm going to leave that as a function. And so now I'm going to say order equals generate edit order. Okay, so now I've created a string order for show me instructions and display the board, edit a square, show possible values for a spot and stuff like that. I've created the string for that. I have not actually executed anything yet, so I need to do some work here. So basically, the first letter of my order is going to tell me what kind of command to execute. So let's do that. Now, what's the question mark for again? I think the question mark was to show the instructions, right? D was for to display the board. E is for edit a square. Now, what I need to do is pull out the coordinates for this and then have an execute. Okay, so I've now generated the order in my interact, a question mark to display the menu, a D to display the options, an E followed by the coordinates and the value to edit an op in a square, an S followed by the coordinates to show the possible values in a given square. And all this string is then passed to my execute. My execute will now execute the order, which is a string. If it's a question mark, it'll display the options. D, display the board. E, it'll pull the row and the column and the value out and edit that square. If it's an S, it'll show the possible values of that square. Let's run it to make sure that it works. It succeeded. I'm going to load board.txt. I'm going to edit. E5. I'm going to put an 8 there. I'm going to display. I'm going to show possible values for B2. It looks like 4 is 1, so I'm going to edit B2, and I'm going to put the value 9 in there, and I'm going to display, and sure enough, I got B2 had the value 9, and E5 had the value 8, so everything works as expected. And of course, I can do the undo and redo exactly the same as I did with the encapsulated invocation, but now I'm passing the order in a completely different paradigm. We can learn more about delegate invocation, encapsulated invocation, and the interpreter in the command passing chapter of the software design textbook.